Welcome to the Simple Harmonic Motion Notes video. Hopefully this is helpful to you in getting through the assignment that we have. I am going to be using some simulations from a website called PhET. If you'd like to go to this website and check out some more of the simulations on your own or play with these simulations on your own, it could be helpful. Feel free to do so. They're lots of fun. So here we go. Let's talk about simple harmonic motion. So you see here with this simulation, we have a spring that is currently in rest and doesn't have anything on it. So I'm going to add a 100 gram mass to it. You'll see that it stretches it out. And it stretches it because, as we learned in the lab the other day of Hooke's law, this dotted line is its equilibrium position, but it stretches it a certain distance based on that force. Remember the Hooke's law, F equals kx. So the spring's constant k of this spring is what allows it to stretch a certain length. Now you'll notice that right now it is in equilibrium. And when it is in equilibrium, the downward force of gravity and the upward force of the spring have to be equal to each other. That's what makes it in equilibrium. Now I'm going to move this spring down, or the line down, to where the spring is at the dotted line. So now this is the new equilibrium point for what we're going to be discussing. So let me go ahead and move in a couple more tools. We're going to bring in a ruler here. I'm going to set it here with it at 30, and this is to measure how far the thing is going to be stretched. So we're going to stretch this out, and I'm going to pull it down to the 40 and let it go. And when I do that, you notice it bounces back and forth between 20 and 40. Let me go ahead and slow this down so that we can see it a little bit better. It bounces between 20 and 40, and this is what we call oscillation. It moves the same distance away from equilibrium as it does above. It goes above and below, the same distance. It's going back and forth. This is what oscillation is. Oscillation is back and forth motion. And when it moves that oscillation from that equilibrium point, it is moving a certain distance. That maximum displacement is what we call amplitude. So the amplitude is the maximum displacement from its equilibrium position. Okay, so I paused my video here for a second so we can talk about this amplitude a little bit more. Let's discuss the fact that it is the maximum displacement. That's for a given situation if I stretch it a certain distance. Don't be confused. It's not the 20 to 40, that's 20 centimeters. But that's not the amplitude. The amplitude is the displacement from our equilibrium position. So it actually only goes from equilibrium up to 20 or from equilibrium down to 40. The equilibrium is at 30, so the amplitude is actually only 10 centimeters. Okay, now that we've discussed amplitude, we're going to talk about something else. When something's oscillating back and forth, it's moving. So therefore, there is speed, there's velocity, there's acceleration, there is a time involved. And that time has a specific name. This period, we use a capital T to represent period in equations because it is a time, and it is the time required to complete one complete oscillation. So we are going to be discussing the period, and we're going to talk about the factors that affect the period of a mass oscillating on a spring. So in order to discuss period, we need to have some measure of time. So we're going to add a stopwatch to our little simulation. And then I'm going to stretch my spring down to the 40 again, give it a 10 centimeter amplitude, and I'm going to let it oscillate back and forth. And then I'm going to need to measure the amount of time it takes to complete one complete oscillation, one down, up, and back down. So I'm going to wait until it gets to the very bottom, back to the top, back to the bottom. So let's go ahead and time that. Down, up, down. So we see that it takes 60 seconds to complete one complete oscillation. That 60 seconds is the period of this oscillating spring. So now that we have the period, let's see what happens if I stretch it longer. If I give it a greater amplitude, it was at 40, now I'm going to stretch it down to 50. That's a 20 centimeter amplitude instead of a 10 centimeter. So now it's stretched a whole lot farther. You'll notice now it goes from 50 to 10. It's moving a whole lot farther, so it should take longer, right? Well, let's time it. Down, down. Oh, look, 60 seconds again. It's the exact same. And part of the reason for that is since it's going down and back up, yes, it's going farther, but since it's stretched farther, Hooke's law tells us that the force is greater, and it's being stretched farther. Force is greater. Newton's second law tells us that greater force means greater acceleration. So yeah, it's stretched farther, but it is also moving much faster. And so the end result is that it takes the same amount of time. So I'm going to stop it from oscillating for a second, and let's see what happens to the period if I then change the mass. I'm going to take the 100 gram off. I'm going to add 250 grams. Now, obviously, when I add more mass, it's going to stretch the spring farther, kx. It's the same k, so it's going to have a greater F, so it's going to get stretched farther. So I'm going to move my equilibrium line and my ruler down to match my new point of equilibrium, and then we're going to do it again. So let's reset the clock, and I'm only going to stretch it down to 40 again since we know that the amplitude does not affect the period. We just proved that. It was 60 centimeters. I added mass. Let's see what happens to it now. Now that it's oscillating back and forth. Hopefully you can tell that it's moving a little slower, but let's time it. And this one took 92 seconds instead of 60 seconds. So obviously the mass makes a big difference, and that should make sense because if I add mass, I am decreasing the acceleration. It's gonna, yes, there's more force, but if I add mass, I'm increasing the inertia, and so it's gonna make a much bigger difference, and so it's gonna take longer. So now let's see what happens if I change the spring constant. Right now it's set at a moderate spring constant, and I want to increase that spring constant. So let's increase it, make it a much stronger spring. You notice my spring gets stronger, and it doesn't stretch as far anymore. So let's find our new equilibrium point. It's got a stronger K, so it doesn't stretch as far with the same mass. So let's find our new equilibrium point, and let's set it in oscillation again and see what happened to the period. So we pull it down to 40, we let it go, it's bouncing, it's bouncing. Let's measure the period again, 38. It's much less than it was previously. So it should be obvious to you, though, that it's moving a lot faster, mainly because that spring constant is much greater. So the restoring force of that, the restorative property of the spring is much greater, so it's going to go quite a bit faster. And so that is the period, and now let's talk about how we're going to explain the period as we move forward. Okay, so let's talk about the period of an oscillating spring and the equation that goes along with it. The equation for this is T equals 2 pi times the square root of m over k, where m is the mass on the spring and k is the spring constant that we get from Hooke's law. So you'll see that the mass and the spring constant are what affect the period. If I increase the mass increasing is in the numerator, so if I increase the mass, period gets longer or bigger. If I decrease the mass, then the period is going to get smaller. If I increase k, then period gets smaller because it's in the denominator, so it's going to make this whole thing smaller. If k gets bigger, then the mass is going to get smaller. So that is the equation for the period of an oscillating spring. T equals 2 pi times the square root of m over k. Now that we've discussed the period of an oscillating pendulum, now we're going to discuss a little bit about the energy involved in a pendulum. So I have the simulation here again. It's cut down a little bit, but we're going to talk about the energy involved. Now, before we get started, let's remind ourselves that gravitational potential energy is the energy stored based off of an object's height. Now let's remember the equation for gravitational potential energy. U sub g equals m times g times h, where U sub g is the potential energy due to gravity, gravitational potential energy. M is the mass, g is the acceleration due to gravity, and h is the height. So when you look at this simulation, this mass is going to have a potential energy the entire time because it's above the ground. And before we go any farther with the simulation, we also need to discuss the potential energy in a spring. Whenever I stretch a spring or compress a spring, I am storing energy in that spring. So it has potential energy because it is stretched or compressed, and we call that spring potential energy. So again, the spring potential energy is the energy stored in a spring when it is stretched or compressed. And it, of course, has an equation that goes along with it, too. And that equation is US, meaning the stored spring potential energy, is equal to 1/2 kx squared. This looks very similar to the kinetic energy equation of 1/2 mv squared, but this is 1/2 kx squared, where k is the spring constant of the spring, and x is the distance it is either stretched or compressed from its equilibrium point. So it's important that you recognize that that is from its equilibrium point. That means when there is no mass attached or no mass hanging on it, no force being applied. So now if we look at the starting conditions here of our simulation, we have a 100-gram mass attached. The dotted line is representing the equilibrium point when there was no mass attached. So now there's mass attached, it is stretched a little bit, and that's why you notice there is a little bit of potential energy here. This is the elastic potential or spring potential energy, and there's a little bit there because it is stretched. And there is some gravitational potential energy because it is above the ground, because the ground is down here. And you'll notice that the total energy is the sum of these two. Now, as the simulation goes, we're going to pull the mass down, and well, I'm going to move the equilibrium line first. Let me go ahead and do that. And if I pull the mass down, you'll notice that the spring potential increases, the gravitational potential decreases, but my total energy increases. Now when I let it go, you'll notice the green line comes. Now it's moving, and when it's moving, it has kinetic energy. But I want you to pay very close attention to that kinetic energy. When is its kinetic energy the greatest? Is it at the top? Is it at the bottom? You'll notice that the kinetic energy is at its greatest at its equilibrium point, at the middle, where it was when it was in equilibrium. Because at equilibrium, all of a sudden, all of its spring potential is zero. So go ahead and stop the simulation. You can go back and replay this again and watch the graphs going back and forth again. But you'll notice that at its highest point, its spring potential was high. At its lowest point, its spring potential was high. And then at its equilibrium point, its spring potential was zero. Now, if we were to ignore gravity here, part of the thing is, let me back the simulation up a little bit. You'll notice at the bottom, the spring potential is extremely large. That's because we're stretched way past its original equilibrium point. If you remember, its original equilibrium point was up here, and that's why its spring potential energy is so high, because it's kx squared, so the greater that x is, the bigger it goes. And then whenever we move the simulation a little bit up, and it goes up, it's going up above its resting point when the mass is on there. You'll see the resting point when the mass is on there. It's going above that, but its original equilibrium point with no mass on it was up here. That's why there's only a small amount of spring potential, because it's not really getting stretched or compressed all that much because of its original equilibrium when there's no mass hanging on it. So don't be confused by that. Most of the time we're going to give you situations where that's not the case, that the dotted line is representing the actual zero of this equation and not another situation. Hopefully that's not too confusing for you. Now that we've talked about oscillating springs, we're going to talk about another simple harmonic situation, a situation of something that is oscillating back and forth, and it's something that you're very familiar with. It's called the simple pendulum. And basically, a simple pendulum is something that swings back and forth from a fixed point. The item at the end of the simple pendulum is called the bob. So let's look at a simulation of a simple pendulum, and I will talk a little bit more about those parts. So you'll see here that this is a pendulum, and it's got a point of pivot and a arm, usually a string or a bar of negligible mass, and then a mass at the end, a heavy mass. This is called the bob. So anytime you talk about the pendulum bob, that is the mass at the end of the pendulum. What makes it a simple pendulum is we ignore certain things like friction and all that fun stuff, and it just swings back and forth. It just simply oscillates. So when we have this, we're going to stretch it out to a certain distance, and when we do that, say we stretch it out to 20 degrees. That 20 degrees is what we call its amplitude now. With a pendulum, the amplitude is measured by the angle from where its resting position is. Its resting position is pretty much always going to be straight down, so that angle that we pull it is its resting position. So if I now release this and let it go, it's going to oscillate back and forth from 20 degrees on each side. So it's going to have that same thing. So what we're going to do now is, this simulation has a slightly different thing. You'll notice that it measured the time it took for it to go from here to there, back, and then back. It just measured one complete oscillation. So one complete oscillation was one complete cycle through. And the time it measured was 2.0198 seconds. So that's the period of this pendulum whenever it is at 20 degrees. So just like with a oscillating spring, the pendulum has different things that affect its oscillation, that affect the period of it. So we see that it was a little over 2 seconds at 20 degrees. Well, now let's move it and increase that amplitude. Does amplitude affect the period of a pendulum? We know it didn't affect the period of an oscillating spring. Does it affect the period of a pendulum? And you'll see that the time is pretty much exactly the same, a little over 2 seconds. So obviously the period is not affected by the amplitude of the pendulum. And the reason for that is the restoring force here, whereas in an oscillating spring, the restoring force was the spring force. In this one, the restoring force is gravity. And gravity doesn't change. So that restoring force is the same throughout the entire oscillation. Now, it's moving farther, it's going to be accelerating longer, so it's traveling faster. Yes, it's going a farther distance, but because it ends up going faster as it moves, the amount of time ends up being the same. So let's talk about the things that do affect it. We had the length, we had the mass. So let's see what happens when we change both of those things. Let's change the length. Let's make this a 2 meter. And then let's stretch it up to the 40 degrees that we did a second ago. So it should be 2 seconds still if it didn't affect it. But we changed the length, and all of a sudden now it's nearly 3 seconds. So increasing the length increased the period, which makes a lot of sense because you're making a much, much bigger arc whenever you increase the length. So now instead of the length, let's try seeing what the mass does. Let's increase the mass. Because again, what's causing this restoring force is gravity. And we pull this up to 40 degrees again. The last one was nearly 3 seconds, so let's see what the period is this time. It's still nearly 3 seconds. The mass did not affect it at all. And that should be obvious to you that the mass doesn't affect it at all, because the mass is dependent upon G, or the restoring force is G, and G, gravity, affects everything. All mass is the same. when we're here on Earth. You'll notice over here, though, the simulation has the ability to be on different planets. So let's see what would happen if we changed G. Let's change G to, I don't know, let's go with the moon. So let's change G, pull it back up to 40 degrees again, and see what happens. Hopefully you can see that it's moving a whole lot slower. And as we measure the period, you go out, back, and back again. This time it took a little over 7 seconds to complete that cycle. So that is the period whenever we change G. So now you should see that the different things that affect the period of a simple pendulum, you have the length, obviously affects the period. The mass did not affect the period. The amplitude did not affect the period, but the value of little g affected the period. So if you change planets, you can figure out g. In fact, this is one of the experiments done on the moon whenever Neil Armstrong and Buzz Aldrin were up there. They actually measured the pendulum and checked to see if the values for g that they thought were actually correct, and of course they were, and they use a pendulum to do that. So now that we've seen the stuff, let's talk about the equation for the period of a simple pendulum. This equation is t equals 2 pi times the square root of L over g, where L is, of course, the length of the pendulum, and g is the acceleration of gravity, just as it always has been. That's an R. And as you can see, if you increase the length, the period gets longer because it's taking a longer arc. If you increase g by going to some other planet, if you increase g, you're going to make the period smaller because it's going to increase the acceleration, so it would be moving faster. Okay, so now we're going to use this simulation here to look at the energy involved in a simple pendulum. You notice here that right now we have potential energy only, and that potential energy is based off of how high it is from the ground. Now, typically we talk about how high it is from its resting spot. So whenever it's at rest, it's down here. We swing it up, and it lifts up some distance, and that's that potential energy. So if we were to set this in motion, as it starts to move, that potential energy is going to get converted into kinetic energy. And when it does that, you see that it switches. Now, most people think that, well, whenever it's here at the top, it's all potential, and at the bottom, it's all kinetic. And unlike an object that is falling, if something's just falling straight down, then at the top it has all potential, and at the bottom it has all kinetic. All right? And whenever it is at the bottom, it has all kinetic, and halfway down they're equal. Well, here we have it where it's halfway down. You know, the amplitude is roughly half of what it was, but you'll notice that the kinetic energy is not equal to the potential energy. It's because that kinetic energy equation is a quadratic equation. It's 1/2 mv squared. And so as it accelerates, the kinetic energy is a squared function, and so it's not an equal trade-off. So at the bottom it is all kinetic, and at the top it is all potential, but it does not move evenly. The value changes quadratically for the kinetic energy, and it's linear for the potential energy. So that's something that's helpful for you to remember and to keep in mind when you're looking at the energy transformations in a simple pendulum. So now let's review some of the simple concepts that we have gone over. First, we have amplitude. Amplitude is the maximum displacement from resting position. So for a spring, this is the maximum x that it gets from the spring constant k and the force. And for a pendulum, that is the angle that the pendulum is swung from its resting position. Now we have period. Period is the time required to complete one oscillation. It is signified by a capital T in equations, and it has the following formulas. For an oscillating spring, the period is T equals 2 pi times the square root of m over k, where m is the mass of the object being oscillated, and k is the spring constant. For a simple pendulum, the period is T equals 2 pi times the square root of L over g, where L is the length of the pendulum, and g is the acceleration due to gravity. We also discussed the potential energy of a spring. That is, of course, the energy stored in a spring when it is stretched or compressed. And for spring potential energy, it is a quadratic equation that has the following formula. U sub S, potential energy of a spring, equals 1/2 kx squared, where k is the spring constant and x is the distance the spring is stretched or compressed from its resting position. Hopefully this helps you find the answers to the review packet about simple harmonic motion, and I hope you have a wonderful day.